In this video today, we're going to talk about how to calculate net electric force in one dimension using Coulomb's law. So when you're trying to calculate net electric force, we want to take into account the signs of charges because that's going to help us draw a free body diagram and help us determine the directions of each force and write a net force equation that's based off of that free body diagram. So we're going to do two examples here where we are calculating net electrostatic force first, and then also considering a situation where we're calculating where we should place a third charge in order to determine where the net electric force would be zero. So in this first example here, we have three charges arranged in a line, so no angles to worry about. And we want to calculate the net electric force on charge 2. So we see the signs of our charges, we see the magnitudes of each charge, and we see the location. So whenever we have a problem like this, first thing that we're going to do is draw a free body diagram for the charge in question. And the trick to drawing the free body diagrams for charges, point charges like this, is to think about, is the other charge exerting an attractive force on the charge in question, or is it exerting a repulsive force? So for charge 2, charge 1 being oppositely charged is going to attract charge 2. It's going to pull charge 2 to the left. And for charge 3, it's going to exert a repulsive force on 2, so it is going to push charge 2 away from it. So both of these forces are pointing to the left. One is an attractive force from charge 1, one is a repulsive force from charge 3. So this tells us whether, basically, if we're going to add the forces together or if we're going to find the difference between them, because we're doing some vector addition here, but it's pretty simple because we don't have to worry about components of force, just the whole force. So when we have our force diagram, we're going to translate that into a net force equation. And to start, we're going to so we have the net force on 2. We're going to say here that we have the force that Q1 exerts on Q2. So again, that's pointing to the left. And we have the force that charge 3 exerts on charge 2, also to the left. So we do sometimes say that any force that points to the left is going to be negative because that's the negative x direction. But since both of those forces point to the left, we just have to make sure that they're the same sign. Whether we make them both positive or both negative, it really doesn't matter as long as the sign is the same because they point in the same direction. So once we've written our net force equation here, we're going to use the Coulomb's law equation to solve, or actually not even quite to solve just yet, but to write an expression that we're going to then solve to find this net force. So for the net force on 2, we have the force 1 on 2. So we have our constant K. We're going to multiply charge 1 times charge 2 and divide by the distance from charge 1 to charge 2 squared, and add that to K Q2 times Q3 divided by the distance from charge 3 to charge 2 squared. And again, our constant K, I'm going to round up a little bit here. We're just going to use 9 times 10 to the 9th newtons times meters squared per coulomb squared. And we are going to plug all those in. But if you want to make your process just a little bit quicker here, notice we have 2 common factors in those 2 terms that we can pull out. So we're writing a little bit less. We can pull out the K and the Q2 to write our net force expression as K times Q2 and then Q1 divided by the distance 1 squared plus Q3 over the distance to 3 from 2 to 3 squared. So let's go ahead and plug in some numbers here and solve for that net force and see if it makes some sense. One thing that I do want to mention here before we get into plugging these numbers in is that when we're using the Coulomb's law equation, we want to imagine that these charges here that we're plugging in, we don't want to plug in any negative signs. We're basically taking the absolute value of that charge magnitude, so you will not plug in negative signs into the Coulomb's law equation. The reason for that being, we want to decide the sign of the force based on our coordinate system and whether we're calling like left the positive direction or right the positive direction. That's how we want to give signs to our forces. We don't want to accidentally get a negative answer from calculating force because we put a negative charge in there. So just be aware of that. Always put positive numbers in for charges and let the direction of the force decide the sign. So in this case, again, I'll just mention this. These two forces, we're going to think of them both as positive because we are choosing that direction to the left to be the positive direction. All right, so let's get into plugging in some numbers here so that we can calculate our net force. So we have our net force for 2, 9 times 10 to the 9th newtons times meters squared per coulomb squared. Our charge 2, again, we're going to keep that positive when we plug it in. Nanocoulombs is times 10 to the negative 9th coulombs. And then we have our charge 1, 3.6 times 10 to the negative 9th, and divided by that distance squared. Okay, and again, just make sure you don't accidentally plug in the position of charge 3. We want to make sure that the distance from 2 to 3, we're putting in as from the position of 0.2 meters to 0.5. So that would be 0.3 meters would be our total distance from charge 2 to charge 3. So if we go ahead and plug that in our calculators, our net force on 2 is 1.3 times 10 to the negative 5th Newton. So that is our answer. That's our net force. So I just want to mention for a quick second here, what would we do a little bit differently if we found that our forces pointed in opposite directions? So an example where that would be the case would be if we had an arrangement like this. So if we had a, let's see here, if we had a negative charge, a positive charge, and then let's say we had another negative charge here, and we were trying to find the net force on that positive charge in the middle. So if that's the case, and again, if this is Q1, Q2, and Q3, Q1 is going to pull Q2 to the left, so that would be our force of 1 on 2. And charge 3 is going to pull Q2 to the right, so that would be our force of 3 on 2. And when we're writing that net force equation for charge 2, now since those forces are pointing in opposite directions, they should have opposite signs. So I'm going to think of the to the right as the positive direction, and to the left as the negative direction. So we would keep then our force of 3 on 2 as a positive force, but we're going to make the force of 1 on 2 a negative force. Again, that's just because they're pointing in opposite directions. So again, we'd like plug all the numbers in according to Coulomb's law equation, do our calculations, but that's the only thing that's different here. We just want to make sure that we make that force diagram so we know what signs to give our forces to make sure that we're adding them or subtracting them where we should be. So for our next example here, I know this question can be a little bit tough to do mathematically sometimes. So we're going to walk through the whole thing. So a lot of times this question comes up where we're trying to figure out where a third charge should be placed so that the net electric force acting on it is 0. And we have this little arrangement here where we have two positive charges, charge 1 and charge 2. We have the magnitudes of those charges, and we know their position. So charge 1 is located at the position of 0 meters, and charge 2 is located at the position 1.8 meters. So there's somewhere in between those two charges, we're going to be able to put a third charge so that the net force acting on it is 0, and it actually doesn't matter. So we don't have the magnitude or the sign of a third charge, but it actually doesn't matter whether that charge is positive or negative, and the charge magnitude doesn't even matter. And once we get into the math, you'll see why exactly that is. So we're kind of just considering the fact that whether that charge is positive or negative, we're going to find a location where the force pointing to the right, I'm just going to call that force 1, and the force pointing to the left, I'm going to call that force 2, are equal in magnitude. Because when we have a force to the right equal in magnitude to a force on the left, that's where we get the situation of the net force being 0. And to translate that now into a math equation, we can say that our net force would be equal to force 1 minus force 2, which is going to be equal to 0 to satisfy the conditions of this question. And of course, that means then that the magnitude of force 1 has to be equal to the magnitude of force 2. So that's the basic idea that we're building off of to answer this question. And so and again, since we don't know what our charge to, whether it's positive or negative, we're just kind of like gonna pick for force 1 and force 2 what exactly we put in for like charges 1 and 2 and charges 2 and 3, or charges 1 and 3 and charges 2 and 3. And you'll see what I mean here as I write down this next part. So for force 1, I'm gonna think of that as this force that charge 1 exerts on charge 3. So I could write that as K Q1 times Q3, our third unknown charge, divided by this distance R1 squared. And that must be equal to K Q2 times Q3 divided by the distance between 2 and 3 squared. All right, so this is our starting point here, and we can start to simplify our equation a little bit. And again, this is where we notice why charge 3, its magnitude and sign don't actually matter. To start off, we can simplify our equation. We notice we see Q3 on both sides. It cancels, so that's why that charge magnitude and sign, it doesn't even matter. We don't need to know it, so don't let that trip you up. We can also even just cancel out K. Even though we know what that is, we don't need to plug it in, we don't need to write it down. So the other thing that we need to kind of deal with here before we start plugging in numbers and solving is we know the magnitude of charge 1, we know the magnitude of charge 2, and we know the distance from 1 to 2, but we don't know what these R values are to wherever this third charge is. That's kind of our whole problem here, is figuring that out. So let's say that our charge here, we're going to add to our picture a little bit. Our charge 3 is going to be a little bit closer to charge 1 than it is to charge 2, because charge 2 is a larger magnitude of charge. So it's going to be somewhere a little bit closer to charge 1. So let's go ahead and call the distance from charge 1 to charge 3, we're going to call that x. And if the distance from 1 to 3 is x, then the distance from 2 to 3 must be 1.8 meters minus x. So we're putting these two different r terms in terms of this same variable x. So essentially we're saying here that R1 is x and R2 is 1.8 meters minus x. All right? And as we get into our math here, we're going to replace R1 and R2 with these expressions for distance, and that's how we're going to be able to solve this. What we're going to solve for is x, and that's going to give us the position of this third charge. So over here on the left of our equation, we have Q1 divided by R1 squared, which we're subbing in x for R1. And on the right, we have Q2 divided by 1.8 meters minus x, and we're squaring that. And to make this a little bit more simple to get started, the first thing that we're going to do is take the square root of both sides. So we have the square root of Q1 over x and the square root of Q2 over 1.8 meters minus x. Next we'll cross multiply, and then we'll go from there. Again, we're just trying to solve for x. We have Q1, we have Q2. So let's see what we do. All right, so after doing all that math, we should come up with our answer of about 0.79 meters. So that means our charge is just a little bit left of center here, a little closer to Q1 than Q2. All right, so I hope this helped you here with doing two things, or a few things. Number one, being able to draw a free body diagram or a force diagram for charges in a line if we're trying to find the net force on one of those charges. We, from there, take our force diagram and translate that into a net force equation that we can use to solve for some unknown quantity. So sometimes you're solving for the net force, you're adding up all the forces on that charge, or maybe you have this other situation where you are trying to figure out where to place a charge so that the net force is equal to 0.